Welcome to AI Peer Review. We're the place where we cut through the noise of the latest AI advancements to really bring you the core insights that matter. Today, we're plunging into something pretty fascinating in the world of vision language models, VLMs. These are those powerful AI systems that combine vision and text understanding, but, well, they often trip over some really frustrating issues. Have you ever seen an AI confidently describe something that simply isn't there in an image that's a visual hallucination? Or maybe answers a question about a photo without, truly looking at it, just guessing from text. Those are language shortcuts, and frankly, they're holding back the true potential of multimodal AI.
Exactly. And these are just minor glitches either. They're critical limitations that really undermine the reliability of the trustworthiness of VLMs. What we've generally seen is that most existing training methods, they tend to focus just on getting the final answer right. This offers a very sparse signal, and it implicitly nudges the model to prioritize language-based reasoning, essentially, thinking over genuine visual perception or seeing. This is what leads directly to these problems. And attempts to just throw more human annotations or maybe distilled labels at the problem, well, they face huge hurdles. Things like cost, the sheer labor involved, inherent biases, and issues with models generalizing to new data. It's tough.
Right. So what if the model could essentially grade itself on its own visual understanding? That's the audacious, really ingenious idea behind an interesting paper, Vision SR1, Self-Rewarding VLM via Reasoning Decomposition. It introduces a self-rewarding method specifically designed to, well, dramatically improve visual reasoning and curb those pesky hallucinations, all without needing any external supervision.
Exactly. The real game changer here is a reinforcement learning framework that cleverly breaks down a VLM's reasoning process. It splits it into two distinct stages. First, truly perceiving the visual information, and second, reasoning with language. And crucially, it then introduces a self-reward mechanism specifically for that visual perception step itself. This whole approach aims to provide a much more balanced and direct training signal, strengthening both the seeing and thinking aspects simultaneously. So today, we'll unpack how Vision SR1 works its magic, why it seems to be so effective, and importantly, what its implications are for you and for building more reliable, trustworthy VLMs in the future.
Okay, let's start by really digging into the problem itself. When we talk about visual hallucinations, what does that practically mean for a VLM in, say, your everyday experience? And why are language shortcuts such a serious concern?
Okay, imagine you show a VLM an image of, let's say, a dog playing fetch, and it confidently describes a fluffy cat sitting peacefully on a red rug. That's a visual hallucination. It's just conjuring elements that are absolutely not present. Language shortcuts, though, they're a bit subtler. A model might be asked, what color is the car in the image? And if, 90% of cars in its massive training data were red, it might just output red without actually looking closely at this specific car in this specific image. It's using its pre-trained linguistic knowledge, its language priors, to guess based on common text patterns, or maybe what it thinks should be there, rather than genuinely engaging with the visual input. It's like it's thinking over seeing.
Ah, I see. So it's not actually looking at the car in that specific image. It's just falling back on statistical patterns from its text training. And you mentioned that current training methods actually kind of contribute to this thinking over seeing bias. How does that happen?
Well, many post-training methods, especially those using reinforcement learning, what we often call RL, and particularly these R1-style approaches that focus only on the final answer's correctness, they only give a very sparse reward signal. Think of it like grading a whole exam based only on the final answer, not the steps taken.
Right. You don't see the work.
Exactly. This sparse signal, especially for the intermediate visual reasoning part, it allows the VLM's powerful language model backbone, its LLM, to just dominate. It finds clever loopholes, it appears to improve, but really it's just exploiting language patterns instead of genuinely understanding what it sees. This can lead to what researchers call reward hacking, where the model basically finds ways to maximize its score without actually solving the problem the way we intended.
I can definitely see how that becomes a problem.
Yeah.
It seems like you'd think a straightforward fix would be to just, feed these models more human-labeled data, or maybe even labels distilled from other bigger models. But even those seemingly obvious solutions hit their own walls, don't they?
Oh, absolutely. Human annotations are incredibly labor-intensive, very expensive, which severely limits how much data we can actually gather and how broadly we can apply it across the huge array of multimodal tasks out there. Then you have distilled labels. They're cheaper, sure, but they often inherit the biases from their source models, and they can struggle to generalize effectively to new, unseen scenarios. But here's the really crucial point. These external signals are static. They're fixed. They can't adapt as the model itself learns and evolves during training. This leads to what we call distributional shifts and, yep, potentially more reward hacking. Ultimately, relying on any kind of external supervision restricts a VLM's true scalability and robustness.
Okay, so this brings us back to Vision SR1. Let's unpack this self-rewarding mechanism. This sounds like it completely sidesteps those issues with external labels and static data. How does it work?
Right. The core idea in Vision SR1 is to empower the VLM to, essentially, reward its own visual perception without needing any outside help. It achieves this by forcing the model to explicitly break down its reasoning process into two clear stages, and it has to produce a structured output. The model generates something like this format: visual perception C, visual perception think answer A answer. So C is the self-contained visual perception bit, C is the language reasoning trace, like its chain of thought, and A is the final answer. The absolute key here is that C, that visual perception part, it must capture all the necessary visual information. So much so that the subsequent language reasoning, T and A, can proceed without looking back at the original image. It needs to be comprehensive and accurate on its own.
Wow. Okay, so the model basically has to articulate what it sees so clearly and completely that it could then answer the question just from its own description. That's where it gets really interesting. How does the self-rewarding check actually play out in practice? Is it complicated?
It's actually quite elegant. It uses a clever two-pass rollout mechanism, all happening within the same VLM. Think of it like a student taking an exam and then immediately grading their own work step by step. So in the first pass, it's pretty standard. The model gets the image and the question pair. It then generates its structured output, the visual perception C, the reasoning trace T, and the final answer A. We then calculate a standard accuracy reward by comparing that final answer A against the correct ground truth. Nothing too unusual there.
Okay, makes sense.
But then comes the second pass. This is the innovative part. We take the exact same VLM and we reprompt it. But this time, we only give it the original question and its own previously generated visual perception. See, that's it. No original image this time.
Okay.
We then ask it to derive an answer just from that. Now, if it can still produce the correct answer from just its own perception in the query, without seeing the image again, then we deem that perception C visually faithful. And that's when a self-visual reward is assigned. It's literally having the model verify its own visual understanding internally, making sure its seeing part was actually good enough on its own. You can see this clever two-pass system illustrated really nicely in Figure 1 of the paper, by the way. It lays it out visually.
That is brilliant. So the model is essentially judging itself on how well its own internal description of the image holds up under scrutiny. And then all these different rewards, the format 1, the final answer accuracy, and this new self-visual reward, they're combined into a single learning signal.
Exactly right. The total reward for any given response is a carefully weighted sum. RQS equals R visual QC plus RANS QA plus RFMTS. So RFMTS is that format reward, just making sure it sticks to the layout. Pretty straightforward. RANS QA is the accuracy reward for the final answer A. And since A comes after the perception C and reasoning T, this implicitly rewards coherent reasoning and the link between perception and reasoning.
Okay.
And then error visual QC is the novel visual reward, the core idea, checking if the perception C was sufficient to answer the question without the image. This provides that direct internal signal for the quality of its visual grounding. It's an ingenious way to instill a kind of self-awareness, if you will, into the VLM's learning process. And, from a deeper, maybe more theoretical standpoint, this reasoning decomposition is absolutely crucial. See, standard RL training for VLMs, if it's only driven by final answer correctness, just RANs it. It offers basically no direct supervision for the intermediate steps, particularly the visual understanding part. It's like giving a student the answer key, but never actually checking their work or understanding.
Right. That's a great analogy. It's like that math student who always aces the multiple choice by just guessing C, but never truly understands how to get the answer. They get the reward, but not for the right reasons. And crucially, they're not learning the actual math. Vision SR1 then forces them to show their work.
Precisely. It forces the model to articulate its visual understanding and then holds it accountable for that articulation. And the real insight here, maybe thinking about it through the lens of mutual information, is quite profound. If you're only rewarding the final answer, the model mostly learns to maximize the connection between the question and the answer, IAQ. It might completely neglect the connection between the image and the answer, IAI. This creates a perfect pathway for those linguistic shortcuts we talked about. By adding this self-visual reward, or CAP, which enforces a high connection between the perception and the image, I see, we're forcing the model to build and strengthen that entire reasoning path. From the visual input I, through the perception C, to the final answer A, it ensures its answers are genuinely grounded in what it sees, not just language correlations. It effectively makes those linguistic shortcuts much harder, or at least less rewarding, to take.
That makes a lot of sense. And to get this entire complex process off the ground, Vision SR1 didn't just appear out of thin air, right? I understand a specific, carefully curated dataset was pretty foundational to its training.
Yes, absolutely essential. A key component is the Vision SR1 47K RL dataset. This wasn't just any random data dump. It comprises approximately 47,000 meticulously collected examples, and these were drawn from 24 diverse open-source VLM benchmarks. As outlined nicely in Table 1 in the paper, it purposefully spans 3 distinct and really vital reasoning domains. Roughly a third is mathematical reasoning, another third is common sense knowledge, and the final third or so is general visual understanding. This extensive diversity is absolutely essential for ensuring robust VLM generalization. You want the model to learn to truly understand a broad range of visual information, not just specialize narrowly.
And what about the cold start problem for training? How do you even begin to teach a model to generate these highly structured self-perceptions in the first place? That seems like a bit of a chicken and egg situation.
It really is, and they tackled that quite cleverly. Before the main reinforcement learning phase, they created what they call a cold start SFT data set, consisting of about 9,000 examples. You can see a summary of this in Figure 2 of the paper. This initial data set was basically crafted by prompting a capable base VLM. They used Quen 2.5 VL7B to generate responses in that specific structured format we discussed: perception, thought, answer.
Okay, so they bootstrapped it.
Exactly. But here's the clever part. This data then goes through a rigorous 2-stage filtration process. First, they just discard any samples where the final answer was wrong, standard enough. But second, and this is crucial, they use a separate verifier model to check if the answer could truly be derived from only the generated caption, the perception C, and the question. This critical step weeds out those false positives where a language shortcut might have accidentally yielded a correct final answer, but the visual perception itself was flawed or incomplete. It ensures the model learns both the format and the correct visual grounding right from the very beginning, before the RL phase even starts.
That's a very thorough preparation. So with this sophisticated self-rewarding framework and the carefully prepared data, how does Vision SR1 actually perform when put to the test against other methods? What did the experiments reveal?
Right, the proof is in the pudding, as they say. The researchers implemented Vision SR1 using Quen 2.5 VL, specifically the 3 billion and 7 billion parameter versions, as their foundational models. They first fine-tuned them on that cold start SFT dataset we just discussed. Then they proceeded to train using multimodal group relative policy optimization, or GRPO, for just one epoch on the full Vision SR1 47K dataset. And importantly, to ensure a fair comparison, they also retrained Vision R1, that's a similar RL approach that only uses final answer rewards on their same 47K dataset. Apples to apples. They also looked at other relevant lines like Perception R1 and Visionary R1, though those often require external human annotations, so the comparison isn't always direct but useful context.
Okay, and what benchmarks did they use to really gauge performance across these different models? Because that's where we really see if these architectural improvements translate into real-world capability gains.
The evaluation was incredibly comprehensive. They really tried to cover the bases, hitting 3 key areas for a holistic view of VLM abilities. First, for general visual understanding, they used benchmarks like MMMU and MMMU Pro, which assess complex cross-modal reasoning and subject knowledge. Also MMBet, which checks for a wide range of integrated VLM skills, things like object recognition, attribute identification, spatial reasoning, stuff like that, and real-world QA and VisNum bench too. Second, for multimodal mathematical reasoning, they really stressed the models, tackling challenges from MathVerse, which often involves deciphering complex diagrams and charts, and also Math Vision for truly tough competition-grade math problems that integrate visuals. And third, crucially, to directly sniff out those hallucinations, they used hallucination diagnosis benchmarks like HallusionBench. This one specifically asks binary yes-no questions designed to pinpoint language-side hallucinations versus actual visual illusion errors. Oh, and for any non-multiple choice questions where you can't just check A, B, C, or D, they even leverage Gemini 2.5 Flash as an LLM as a judge. This provides a pretty reliable proxy for human judgment on open-ended answers.
Wow, that is comprehensive. So what were the results? Did Vision SR1 live up to the hype?
The results, which you can see laid out clearly in Table 2 of the paper, are quite compelling, I'd say. Vision SR1 consistently outperformed the baselines across the board. For instance, with the larger 7B backbone, it achieved an average score of 58.8%. That's significantly better than Vision R1, which scored 57.4% on the same data, and also better than standard supervised fine-tuning, which came in at 55.1%. And even with the smaller 3B backbone, Vision SR1 achieved a solid 52.9% average, still outperforming all the comparable baselines. These results aren't just, tiny incremental improvements. They really do validate the effectiveness of the self-rewarding approach, showing genuine and quite significant gains in overall VLM performance.
That's a strong showing, definitely. But sometimes, when you introduce a complex new mechanism like this structured output and the self-reward, it's hard to tell which part is doing the heavy lifting. Did they perform an ablation study to really isolate the impact of the self-reward itself? Was it just having that structured output format, or did the self-reward component truly make the critical difference?
That's an excellent and crucial question, and yes, they did exactly that. Table 3 in the paper presents those critical ablation results. They directly compared the full Vision SR1 against a version without the visual perception self-reward. Now, this without self-reward model still followed the exact same structured output format. It produced the visual perception, the chain of thought reasoning, and the answer. But it crucially lacked that specific self-reward signal for the quality of its visual perception C.
And the outcome?
The outcome was clear. The ablated model, the one without the self-reward, consistently showed worse overall performance across nearly all the benchmarks compared to the full Vision SR1. This proves pretty definitively that the self-visual reward is critical. Its benefits go far beyond just having a structured output format. It's about having the model internally validate and reinforce its own visual understanding step. That reward signal matters.
Okay, that isolates it nicely. That's a key takeaway. Now, you also introduce a fascinating new metric in this work, the language shortcut rate, or LSR. Tell us about that and what it revealed about how these models are truly learning, or perhaps how they're managing not to learn visually.
Right, the LSR. It's presented in Table 4, and it's designed as a diagnostic tool for exactly that issue. It tries to quantify how often a model produces the correct final answer, despite having an incorrect or maybe just incomplete visual perception. Think back to our math student analogy. If the student gets C right, but shows completely wrong or nonsensical work, that's a shortcut. A high LSR indicates the model is leaning heavily on its language priors, its textual knowledge, rather than genuine visual understanding from the image.
Has it calculated exactly?
It's defined pretty simply as the number of samples where the model had an incorrect visual perception, C, but still managed to get the final answer, A, correct, divided by the total number of samples. So naturally, a lower LSR is much better. It signals less reliance on those potentially misleading linguistic shortcuts.
And what did it show for Vision SR1?
A key finding was that Vision SR1 consistently lowered the LSR compared to the model trained without the self-reward component. For the 7B model, for instance, Vision SR1 achieved an average LSR of 6.7, whereas the ablated version, the one without the self-reward, had an LSR of 7.9. This directly shows that adding the perception reward actively reduces the model's reliance on language shortcuts. It forces the model, or at least strongly encourages it, to truly see the image and ground its understanding there first.
And you found, interestingly, that this language shortcutting was particularly high in the multimodal mathematical reasoning tasks. That's quite a specific and critical insight. It suggests maybe a deeper problem in how we've been training models for those types of visual reasoning tasks.
Yes, that was a very significant observation, vividly demonstrated in those LSR results in Table 4. Mathematical reasoning tasks, which often involve deciphering complex diagrams, charts, maybe geometric figures, and logical steps presented visually. These tasks revealed a consistently higher tendency for the models without the self-reward to shortcut their way to the answer. And this really raises an important question, maybe even a flag, for a lot of previous work on RLO training for VLMs, especially in these math domains. Are these methods truly improving the model's visual reasoning capabilities, its ability to interpret the diagrams? Or are they perhaps inadvertently just enhancing the model's ability to guess answers based on linguistic priors, patterns in the question text, without actually looking properly at the visual information in the diagram itself?
That's a crucial distinction.
It is, and Vision SR1 directly tackles this by making that visual perception step explicit, structured, and most importantly, self-verifiable through the reward mechanism. It's making sure our math student model isn't just picking C without genuinely showing its visual work.
Right. One final area the paper touched on. How did this whole training strategy affect the model's text-only reasoning capabilities? Sometimes, focusing heavily on one modality, like adding this visual self-reward, can unintentionally degrade performance in another modality, like pure text tasks. There's sometimes a kind of forgetting effect.
That's a valid concern, and they did explore it. Table 5 in the paper delves into this directly. We did observe that multimodal RL training, even the Vision SR1 approach, can sometimes lead to a slight degradation in text-only reasoning performance, particularly in mathematical reasoning tasks performed purely on text. This actually aligns with some recent findings in the field on what's been termed text-only forgetting when doing multimodal training.
Okay, so some degradation is possible.
Yes, but here's where Vision SR1 showed another advantage. Compared to the baseline Vision R1, which only rewards the final answer, the Vision SR1 method proves significantly more effective at mitigating this degradation on text-only mathematical benchmarks like Math 500 and GSM 8K. And furthermore, it actually yielded larger gains on general text-based knowledge tasks such as MLU Pro and Super GPQA. So the takeaway seems to be that by explicitly separating and individually optimizing for visual perception and language reasoning, Vision SR1 helps to preserve, and in some cases even enhance, those text-only competencies alongside its significant multimodal improvements. It leads to a much more balanced and holistic learning outcome.
That's really interesting. So wrapping this up, what does this all mean for you, our listeners, and maybe for the future of AI development more broadly? Vision SR1 isn't just another, incremental tweak. It presents a genuinely compelling path forward for vision language models, it seems. By intrinsically rewarding the model for its own visual perception, making it check its own seeing, it tackles these core issues like hallucinations and language shortcuts head on. And the result appears to be demonstrably more reliable, more trustworthy, and genuinely reasoning AI.
I agree. This work truly opens up several exciting avenues for future research as well. One obvious direction is exploring even more explicit perception rewards, perhaps directly rewarding the internal visual embeddings rather than converting them to text first, potentially reducing any information lost during that conversion. Another really fascinating direction is developing truly self-evolving VLMs. Imagine models that can reward both their visual perception and their final answers without any reliance on external human labels whatsoever. That would be a VLM that can continuously refine and improve its visual grounding purely through internal self-generated feedback. That's quite a step.
That sounds like science fiction almost. And crucially, stepping back a bit, this research really highlights the ongoing fundamental need for us as a field to disentangle true visual grounding from this clever shortcut learning we've discussed. We need better benchmarks, more robust analyses, maybe like the LSR metric, to ensure that the impressive accuracy improvements we often hear about in VLM papers aren't just, clever exploitation of language patterns, but represent actual deep advancements in visual understanding.
Indeed. Establishing a stronger foundation for measuring and actively mitigating these language shortcuts will empower the entire research community to design more principled, more effective training objectives. Ultimately, this will lead us to building VLMs with deeper, more reliable visual reasoning models that you can truly trust to see what's actually there in an image or a diagram.
So could self-rewarding mechanisms like Vision SR1 be the key to unlocking truly intelligent, multimodal AI that finally sees as deeply and reliably as it thinks? That's definitely a provocative thought to leave you with. This has been AI Peer Review. Thank you for diving deep with us today.